Alright, so today I'm going to be explaining this important paper with the title From Theory to Practice, Rethinking Green and Martin Kernels for Unleashing Graph Transformers. This ICML paper in 2025. Graph transformers have emerged as powerful alternative to message passing neural networks. Yet their performance heavily depends on effectively embedding structural inductive biases. So we introduced novel structural encodings grounded in a rigorous analysis of random walks, leveraging Green and Martin kernels that have carefully redefined for AI applications while preserving their mathematical essence. These kernels capture long-term behavior of random walks on graphs and allow for enhanced representation of complex topologies, including non-aperiodic and directed acyclic substructures. Empirical evaluations across 8 benchmark datasets demonstrate strong performance across diverse tasks, notably in molecular and circuit domains. We attribute this performance boost to the improved ability of our kernel-based SE structural encoding to encode intricate structural information, thereby strengthening the global attention and inductive bias within the graph transformers. So you can always look at random walk on graphs as a stochastic process, because we can define this transition probability, that is the probability of a random walk starting from node X moves to node Y in the next step. So if we do convolution of P with itself, it follows like this. So if G is a finite graph in n nodes, P can be represented by just an n by n matrix, where D is a diagonal matrix. And we define sequence spaces by a set of sequences. So we simply denote by omega the union of all these sequence spaces. And so we can define now our probability measure over such sequences. For example, what is the probability that a random walk starting at node X passes through U1, UK? So starting from X passes through U1 and UK. What is the probability? And so we can define this probability measure. Now we introduce Green kernel and Martin kernel, which are essential tools for understanding random walks on graphs. The green kernel represents the expected number of visits from one node to another, while Martin kernel describes the probability of reaching a specific node from another within a finite number of steps. One can formulate both kernels as follows. So here L is just a counting function, and this tau here is the first hitting time. So here is their methodology. We construct this GKSE and MKSE with the dimension K like this. So this is the finite state Green and Martin kernels respectively. So the finite step Green kernel can be calculated using this recurrence. First, observe that traditional Martin kernel M is defined by g of x, y divided by g of y and y. The finite step Martin kernel with the first hitting time map can be computed by this formula. So to apply the first return time map in finite step Martin kernel, we use the following modification. Although the finite step Martin kernel computed here may not exactly match equation 9 that I showed you here, this finite time Martin kernel, it provides a close approximation. So it's just a good approximation of what I showed you. The following theorem ensures that the approximation is good. The approximation is accurate. So we have the real value that we want to seek, but this is the approximation. So there is an upper bound to the difference. So they did experiments on zinc and MNIST and CFAR. Zinc and QM9, these are data sets for graph generation as well as graph property regression. Also, they did experiments on peptide function and peptide struct. So they compare gated graph convolution to their, so you see there's some improvement. And these are visualizations on a fluorescent molecule for k steps ranging from 1 to 5. In each graph, the thickness and color intensity of edges represents the magnitude of the corresponding SE values, with higher value indicating thicker and darker edges.